Hello, my dear student. Welcome once again the course number 1, that is the electrodynamics in M.Sc. Physics. In previous video, we will discuss the magnetic interaction between two current loops, that is the Ampere force law, and first is the energy relation in quasi-stationary current system. In this video, we will discuss the 2 points, that is the first is the energy stored in a magnetic field and second one is the energy stored in a electric field. Let's see the first point, that is the energy stored in a magnetic field. Let's see the figure. We have obtained the expression for the energy stored in magnetic field. Let's see the figure. Let's consider that inductor and that inductor L is the inductance of that coil. Consider a inductance, or that will be the solenoidal coil, and that inductor L is the inductance of that coil. Okay, and this inductance is connected to that cell through that key. Okay, and next let's see that switch is on. Then this current is passed through that coil. Switch is on and that current I is passed through that coil. Then this magnetic field is induced in that coil. Magnetic field induced in that coil. The current will flow for this solenoidal coil or this inductor. The magnetic field induced in that coil. Magnetic field is induced in that coil. Then this magnetic field is not constant. Magnetic field is not a constant, because this current will be vary, or current will be increasing. And that magnetic field will do not constant. That means this magnetic field will be vary. Will be vary, and then that induced magnetic field is vary. That means this magnetic flux will be vary. That induced magnetic field will be vary. That means this is the magnetic flux will be vary, and then that change in magnetic flux that indicates the induced back EMF in that inductor coil. This change in magnetic flux that indicates the induced back EMF in that inductor coil. Okay, then, or this is known as that induced back EMF, or it is known as a induced current, and the direction of induced current is that is the opposite of that applied current, and this is the induced current will be produced. But the direction of that induced current is opposite to that of the applied current. Okay, that the working is when we apply that, or a switch is on, then current is passed through that inductor, then magnetic field induced in that coil. Then current will be increasing. Then this induced magnetic field will be changed. And that's why that change in induced magnetic field, that means that magnetic flux will be changed, and that change in magnetic flux that indicates the induced back EMF in that inductor, or it is simply known as a induced current. And this is expressed in that relation E is equal to minus L di by dt. E is equal to minus L di by dt. And or this is in that coil, in that solenoidal coil or that inductor, the induced current will be produced. But this induced current is opposite to that applied current. Means the direction of induced current is opposite to the applied current. That's why some work will be done. And that work done, this cell has to be work to be done. Why? Because that induced current is opposite the applied current. That's why some work done will be done, and that work done is the dW. That work done is the dW minus E into dQ. That work done, some work done will be done because that induced current is opposes the applied current. Then that applied current when it do not easily flow, that's why the work will be done, and that work will be done. Who is the work will be done? That cell will be work is the done, and that work done is the dw is equal to minus E into dq. This negative sign indicates that the that induced current is opposes the applied current. Okay, then this work will be done. Then this cell, that cell, the some energy, because this work done, who is the work done? That is the cell is the work done. That's why some energy will be lost. That's why some energy will be lost, and that loss of energy that's stored in that solenoidal coil. That loss of energy is stored in the solenoidal coil in the form of magnetic field. In the form of magnetic field. Okay? बघा की वर्क डन कोणामुळे होतंय, कशामुळे होतंय की आता इथे काय आहे की इंड्यूस करंट काय करतो, अपोज करतोय अप्लाइड करंटला. मग काय होणार आहे की आपल्याला काही वर्क डन होणार आहे, इथे वर्क विल बी डन. पण ते वर्क कोणामुळे डन होतंय, या सेलमुळे होते. काय होतं, या सेलमुळे. मग अशा वेळेस काय होतं की या सेलची काही एनर्जी काय होते, लॉस होते. काय होते, लॉस. अँड जी एनर्जी लॉस होते ती एनर्जी लॉस होते इन द फॉर्म ऑफ एनर्जी, बट कुठे, या इंडक्टरमध्ये होते एनर्जी इन द फॉर्म ऑफ मॅग्नेटिक field, and that's why this work done will be dw is equal to minus E into dq. Then we have to obtain the relation, that is the energy stored in a magnetic field, and that energy loss होते. ती जी लॉस झालेली एनर्जी ती कुठं स्टोअर होते, ह्या इंडक्टर मध्ये, बट इन द फॉर्म ऑफ मॅग्नेटिक field. That energy is in the form of magnetic field, and then we have to obtain the expression for energy stored in a magnetic field. Let's see that these two equation. E is equal to that induced back EMF E is equal to minus L di by dt, and that work done dw is equal to minus E into dq. Then we put the value of E in that equation, and therefore dw is equal to minus will be plus L di by dt into dq, or equation are this dt will be divided by dq divided by dt. We write d L di dq by dt, and therefore dw is equal to L dw is equal to this dq by dt. Dq by dt is the current, and that L di. Dw is equal to Li di. This is the small work done with as compared to small charge dq. But we calculate the total work done. We calculate the total work done in integrating dw is equal to integration. Then limit are 0 to I. Limit are 0 to I, because current, firstly current will be 0, and switch is on, current will be increases, and this Li into di. This derivative integration will get cancelled, remaining W is equal to, capital W is equal to integration. L will be outside the integration, 0 to I into di. Then therefore W is equal to L 0 to I integration I di. We use the formula integration x dx is equal to x raised to n plus 1 divided by n plus 1. Then we write directly integration, and that integration is I square divided by 1 plus 1, because power is a 1, the 1 plus 1 2 divided by 2, 0 to I. Then we put upper limit minus lower limit, that L, upper limit is I and lower limit will be 0. That means second term minus throughoutly 0. That means we put I square divided by 2, and therefore, and this is minus 0, lower limit will be 0, minus 1/2 Li square. That work done W is equal to 1/2 Li square. Okay, but we know in previous class, that is the TY base C, we studied the work done is also work done is similar to that potential energy. Work done is, let's see, this point is the electric potential, at a point charge. In that point, we will study the work done is same as the potential energy, or this work done is equal to the potential energy, and that work done is equal to U. That means that U is equal to 1 by 2 Li square. This is the energy stored in a magnetic field. That is, U is the energy or potential energy is equal to 1 by 2 Li square. Okay, this is the expression. Then in next, this is the energy stored in a magnetic field, but we calculate the energy density. We calculate the energy density in a magnetic field. Energy density in a magnetic field. Then what is mean by energy density? What is meant by energy density? Let's see. The energy density is defined as the energy stored per unit volume, and that energy density, that is the UB, we denoted as a energy density in a magnetic field is denoted by UB, and this energy density is defined as a energy stored per unit volume. Energy stored per unit volume. This is the definition of energy density. Energy density is a energy stored per unit volume is known as a energy density. Then we consider the one inductor or solenoidal coil, and N is the number of turns, and that L is the distance and having area A, and that current I will be passed from that inductor coil, then magnetic field induced in that coil, and that magnetic field is equal to B mu naught N into I. This magnetic field is expressed in the relation B is equal to mu naught N I. Mu naught N I. Then we calculate the energy density, that mu B is equal to energy stored. This we calculate that relation 1/2 Li square divided by volume. Then volume is equal to area into that length, and that A into L. Mu B is equal to 1/2 Li square divided by A L. But the value of inductor in TY class we have studied, L is equal to mu naught N square A L. Value are the mu naught N square A into L. That is the value of inductance, and our equation are this 1/2 Li square divided by AL. This equation is simply as this L upon L, and this I square divided by this 2 will be transform of denominator, and equation are L upon L, capital L upon L is equal to 2 will be cancelled, 2 will be transformed in denominator, I square divided by 2A, and L is that inductance value is mu naught N square AL, and therefore L this is multiply transform it will be the divide mu naught N square A. Then put this value in equation, that mu B is equal to L upon L mu naught N square A I square divided by 2A. A get cancelled, remaining term mu B is equal to mu naught cancel N square I square divided by 2. I square divided by 2. This equation. Then in next step, multiply and divide mu naught, multiply and divide mu naught, then equation becomes that energy density mu B is equal to multiply and divide mu naught square N square I square divided by mu naught to mu naught, multiply and divide. But mu naught Ni is equal to that magnetic field is mu naught Ni, and this is square, that means that therefore this mu B is equal to B square divided by 2 mu naught, and mu B is equal to 1 by 2 B square divided by mu naught. Mu B is equal to 1 by 2 B square. Then put B is equal to mu naught H, and therefore mu B is equal to 1 by 2 B square is equal to that B is equal to mu naught H, that means mu naught square h square divided by mu naught. This one get cancelled and therefore mu b is equal to 1 by 2 mu naught h square. Mu b is equal to 1 by 2 mu naught h square. This is the energy density, that equation, that W or V is equal to 1 by 2 Li square. This is the energy stored in a magnetic field. Sorry. But this equation mu B is equal to 1 by 2 mu naught H square. This is the energy density in a magnetic field. Energy density in a magnetic field. This is the simple expression for energy stored in a magnetic field. In that next point, we will discuss the energy stored in a electric field. Okay. Thank you. Next lecture, we will discuss that point, energy stored in a electric field. Thank you.